Alright, so this part of the notes, you're going to be able to recall stuff from pre-calc, and you're going to incorporate it with things that you're now using in calc, and the objective is to do this. My goal is to graph functions without using the graphing calculator a lot faster and a lot more exact than what I would if I was in pre-calc. Remember that unit that you guys graphed and you didn't use a calculator and you were doing everything depending upon whether the highest degree was odd or even, whether the coefficient of that was positive or negative, and you got a good estimation as far as what did the graph look like. If it was a positive coefficient, I know it went up as you went to infinity. If it was a leading, the leading degree was an odd number, it would be the opposite, and it would look something like that in between. If it was an even number like 2, 4, 6, 8, 10, and it was positive going this way, well, ultimately, it would be positive going the opposite direction. Things of that nature that you did in pre-calc, we're now going to use calc knowledge so that we can be more exact, more descriptive, and it's a more close representation of a graph that it would be if you were to put it in your graphing calculator. The ultimate goal to do these problems near the end of the period will be about between 5 and 7 minutes, depending on how fast you are able to acquire information. But I'm warning you right now, there are a lot of subtle details. Okay, a lot of subtle details to where if you know, it's easy. If you don't, you have a little bit of review to do. Okay, so in fact, the subtle details that we're going to discuss, if you are able to tell me what they are before I ask you, and you'll see what I'm talking about as we go through the notes, of course I will give you bonus points, and there are a lot up for grabs. So here we go. Alright, this is pre-calc knowledge, and this is algebra 2 knowledge. Former knowledge that is not as higher level thinking as calc is, but that we can show when something is increasing or decreasing. For instance, if I have an x value that is less than another x value, and for that pertaining x value, its y value is less than that other guy's y value, I'm looking at a graph that looks like this. And if I draw something in between them, this graph is increasing. This goes without saying. All this is saying is that this is y value is less than this y value as I'm going from left to right. And you can see that right now. Vice versa, if I have a decreasing, it's going to be the other way. If I have this line, or it can be a curve, we're going to discuss that here in just a bit. If I'm going left to right, and the first one is bigger or higher than the second y value, it's obviously going to decrease. Okay? Now, keywords. Intervals. Between 2 points, not inclusive. There's a hint right now for what we're going to talk about today. That's when you're increasing and decreasing. Now, what I want you to do with this is I want you to throw that out the window because you're not going to use that justification in calc. You're going to use a more sophisticated justification as far as when a function is increasing or decreasing. It's all about something you've been doing for the whole year now, the derivative. If the derivative is greater than 0, which I want you interpreting that as the derivative is what? Positive. Who said that? Positive, right? If the derivative is positive, then f is increasing. Now, something right off the bat that I want you to be aware of is that you have 3 different case scenarios. The derivative can be positive, it can be negative, or it can be 0. So if it's positive, we said it was increasing. If it's negative, we're going to say it's decreasing. And if it's 0, it's going to be constant. Now, if I'm looking at something right now, what's the subtle thing that you're looking at of how you're describing f of x? What should stand out at you right now as far as you're seeing the slope, right? So this is what I want to do. I'm going to do an analogy real quick. And I'm only using you as an example. No, you're not like this, but I'm only going to use it as an example. Let's say that we have 2 things. En is f of x. Okay? And I'm going to use Harrison as f prime of x. Now check this out. my goal is to graph what? En. My goal is to be able to graph a function that I'm given, f of x, but I'm not going to use it by trying to identify En level knowledge. I'm not. We threw it out the window. We're trying to find out how can I graph En by analyzing the things and the details that Harrison, the derivative, is giving me. You understand? Right off the bat, this should be a little bit uncomfortable because you're never going to truly know what the function is until you've examined everything and extrapolated all this information from the derivative function. And there's a lot, but the good thing is it's repetitive, so it's easy after that. So, and I know you don't do this, but let's say I'm going to interpret this as the tattletale. I've never met En ever. And I want to discover what he looks like, what he is like, whatever he does, the graph essentially, and I'm not allowed to ever see him. He's behind a wall. The only picture in my mind that I can get about En is through Harrison. So the more details I obtain from him, the better I can assume, all right, he's probably like this. So when I meet him, I'm like, dude, that's pretty good. It's exactly like Harrison said he would be. Otherwise, Harrison's way off, and he gave me this way bogus information. You understand? That's the goal. Now, if I'm looking at the derivative, there are certain key things that the derivative will give me that they all tie in. And if you're understanding throughout notes, you'll see how everything just ties in immediately at some point in time. And I'm talking about you're able to interpret two different things at the same time, and you're piecing together and you're building the f of x graph. Here we go. Critical numbers. What did we say they are? Zero and undefined, right? And we said zero and undefined. We said when the slope is zero, those are whenever it is at a relative max of some curve, right? When are they undefined? What did we say? Vertical asymptotes, or not vertical asymptotes. Vertical tangents, cusps, and endpoints. Okay? Those are where it's undefined. Now, f is differentiable on the interval. And when f prime of x is changing from positive to negative, and please put that in your notes. When f prime of x changes signs from positive to negative, we're identifying a relative max. How does that make sense? Well, we said in the last slide, if the derivative is positive, what is f of x doing? Increasing. If the derivative is negative, what did we say f of x is doing? Decreasing. Do you notice how this, true or false, has to exist? True. It has to exist at a point, otherwise it doesn't have a y value that is showing you that is the relative max. Okay? So increasing to decreasing, relative max. Why not absolute? It doesn't account for the endpoints. It doesn't count for other critical points, right? But definitively, we can say that it could be a relative max. Okay? So good, small little details. Let's go ahead and keep going. The second one. When the derivative is changing from negative to positive, is this changing from a decreasing to an increasing? That's already going to show you that it is a relative minimum. Goes without saying, right? Pretty straightforward. All right, so now let's go ahead and jump to the problems. Our goal is to identify on f where the function's increasing, decreasing, to identify relative max and mins, and then use justification, and this is the part that most people struggle with, if they do struggle in this unit, and then sketch the graph. So here we go. I'm given f of x. Let's solve this first. Okay? So what am I going to do? Derive it. Here we go. So f prime of x is equal to x squared minus 2x minus 3. What do I do next? Set it equal to 0. Why? Because we're looking for the critical points. Can I set it equal to undefined? No, because it is not a rational function. Okay? So here we go. 0 is equal to, let's factor this out. You've done it since Algebra 2. This is why you learned the skill. What are the factors? Yep, x minus 3, x plus 1. So my critical points are negative 1, 3. Cool. Now, are those my only critical points that I found from the derivative? Yes. Could there be other critical points like we did last class with this particular problem? No, there aren't any endpoints, right? This says they didn't establish any endpoints. So this is forever to the left and forever to the right. So here we go. Next step that I want you to do is draw a representation of the first derivative with a number line. Because we're about to use these critical points, and I'm going to put them in ascending order because I'm about to do a sign test with some intervals. And I see a lot of you already, oh, that's what we're doing. Okay, and that's good, that's fast. How many sign tests are we doing? 3. So we have 2 critical points, we're going to have 3. We have 5 critical points, we're going to have 6 sign tests. Okay, so here we go. And pick good numbers. Obviously, the number that you would probably pick in the first interval would maybe be what? Negative 2, right? In the first interval. So in the first interval will be, no worries, negative 2. So what I want you to do, trust me, this is a lot better than dreads and a lot better than related rates. Right here, I want you to identify on the factored form after you derived and set it equal to 0. That's where you want to plug in these numbers, okay? Don't try to do it over here because it's just more work. You can do it faster at different places. Let's put in a negative 2 right here and right here. And I don't care what numbers they equal. I just care about their sign. All right, so negative 2 minus 3, positive or negative? Negative. Negative 2 plus 1. Negative. Multiply those two and I get a positive. And I'll put a positive right there. Okay? Now I'm going to try another number in the second interval. What would you suggest? 0 is the best number. Because the first one is negative. The second one is positive. So the product is negative. Good. And then the last one, let's say 4. First one is positive, positive, and then positive. Here we go. Here's our little cheat sheet. The more descriptive that you do this, and this is the questions that I'm asking Harrison with, not with our analogy, the faster it is that you're going to be able to graph the graph here in just a bit. What was the slope at negative 1? 0. I'm going to put right here 0, and I'm going to put HT. HT for what? Horizontal tangent. Nice. So let's keep going. Whoops. Alright, so what I'm doing below it is showing at these points the derivative is 0 and it's horizontal tangent. Why do you think I put horizontal tangent? Yeah, like what would it come to? A horizontal tangent could occur at a cusp. True or false? False. Horizontal tangent cusps are non-differentiable. A horizontal tangent could occur at a vertical tangent. False. The vertical tangent slope is what? Undefined. A horizontal tangent slope is what? 0. But they both are critical points. True or false? True. Okay? So let's keep going. On top of the signs, I'm putting in INC, DEC, and INC. What we just learned, right? The first derivative says that f of x is increasing on that interval, decreasing on this interval, increasing on the last interval. You with me? And then I have horizontal tangents at negative 1 and 3. Any questions so far that we have? Okay, so now I'm going to go ahead and start answering. So I've done the work. This is how you will start answering. Per first derivative test is the very first thing that I want to do. Now, please understand what the first derivative test truly means. Because I don't want you to do this as some people did last year, and they went in autopilot mode. Every question they got, they started it with per first derivative test. And they got a lot of them wrong because they weren't all first derivative tests. Another one that we could have done that we worked on last time was what? candidates test. So the candidates test looked at something different. It looked at the endpoints, the critical points, and they put it on f of x, that table that we did, and it found the y values. That's a different test. This first derivative test is dealing with the first derivative to see when is it increasing or decreasing. Okay? I'm going to come back to that to see if you're understanding what first derivative test truly is here soon when I ask you other type of questions. Here we go. F of x increases on or at, or does it matter? On. Can you increase at a point? No. Because it's a single point. You increase between points. There you go. You don't increase. So every time I put increase or decrease, I can always put what around these numbers? Parentheses. No brackets ever on increasing or decreasing, because you cannot increase on an endpoint. Okay? So here we go. Increases on what? You tell me. Negative infinity to negative 1. Union. Yeah, no, you're right. 3 to infinity, right?
Oh, I thought you meant.
Okay, so now f of x decreases on, yes, negative 1 to 3. Now let's answer the next part. Relative max at, so this is different, at what? I'll be a little bit more exact. There you go. Relative max, yep, at x is equal to negative 1. Now here comes this part. Why? Justify that. Yes. You're right, but I would prefer if you write it and put down f prime of x, okay? Because f prime of x changes signs. Is that enough? Why? Why do you have to do that? Yeah. There's two different types of relatives. There's one or another, right? I know that you knew it, Ian. All right, so looking at this, let's finish it out. Changes signs from positive to negative. There will be something that I will give you here soon. It's called test of concavity. You don't have to say positive, negative, or negative, positive. I want you to understand the subtle difference later. All right, so relative what? Min at what? Say again? X equals 3. Why? No, not it. F prime of x, right? Because it could be f prime, f triple prime, f quadruple prime. Yes, because f prime changes signs. Yeah. Specifically from negative to positive. And we're not done yet. The only thing we have to do now is sketch the graph. So here comes the weird part for some, and people were able to think out of the box, they get it pretty fast. Here we go.
You found the sign change from when we did the numbers test or the line test? The sign check, sorry. Like you found that change from positive and negative from that right there?
Here we go. I found this information specifically with this stuff from this number line thing, as she called it.
Sorry.
What is it called? What did we do? What I just circled is what? The first derivative sign test. Okay? The first derivative test aims to find this. If I want to know when a function is increasing, look at its derivative. So if I come to you and I ask you, okay guys, I want you to tell me, when is the acceleration of a particle in space increasing? What do you analyze? Its derivative. It's what derivative? It's first derivative. So when I say first derivative test, I'm saying one level of reality into from where you're at. Do you understand? Well, let's go back to the analogy. He's f of x, he's f prime of x. If Ian is f of x and he's acceleration, and I'm trying to see when is Ian increasing, I'm not going to look at Ian, because sometimes I can't see that graph in real life. I'm going to look at his derivatives. His rates of change will tell me what he's doing. So I'm not looking at f prime of x. What am I looking for? What do I have to observe if I'm trying to see when Ian is increasing or decreasing? F triple prime of x. You notice that? F triple prime of x, listen, is the acceleration's first derivative. So if En is f double prime, and I want to see when is this increasing or decreasing, I don't analyze f double prime. I do the first derivative test, and I analyze this guy's first derivative, which in this case is the third derivative function.
We just made up that En was f prime of x, right? Or f double prime.
Yeah, we just made that up. That's just an analogy, so that you truly, because it was good timing when she asked it, so you could really understand what the first derivative test is. Do you understand? So if I want to say, hey, when is the fifth derivative increasing? Well, don't look at the fifth derivative. Close your eyes. Look at its tattletale or whatever, however you want to interpret it. Fifth derivative's tattletale, its first derivative is the sixth derivative. When that's positive, that's when the fifth derivative is increasing. Always one level away. That's the hard part. You're not going to look at what you're seeing is increasing or decreasing because it won't tell you. Your goal is to see and come up with that function eventually in real-world application. Okay, here we go. We'll come back to that. So, let's graph. Piecing all this together, one thing that I'd probably want you to figure out is being able to talk and describe what's going on position-wise, f of x, and f prime of x at the same time. So I want you thinking of these two levels simultaneously. Here we go. We know there's a critical point at x equals -1. What's its position if x is -1? Use a calculator if you need to. Put the calculator in here. -1 cubed is -1. Times 1/3, -1/3, right? Let's put minus +1 plus 3 plus 2. So with the calculator, or however you want to do this, this is -4/3 plus 5, right? So plus 15/3. So it's going to be a positive 11/3. That's just fractions, guys. That's just adding fractions. So my position is 11/3. That's almost 4. That's 3 point something, right? So here we go. 1, 2, 3, 4. At -1, we know there exists a point there. Okay? Let's do the other one. 3. Let's put it into the position function. So if I put in the position function, 27 divided by 3 is 9. Minus 9 is 0. Minus 9 is -9 plus 2, -7. So at 3, we're going to be at -7 way down here. Do you follow? Okay, those are positions. Those are my pivot points, if you will. What's another pivot point or something on the position function that I can draw right now? Wait, what? Yeah, say it though. Y-intercept. What is it? 0, 2, right? Plug in 0 where you see all these x's, and the only number left over is 2. So the y-intercept would be 0, 2. See it? Now, here we go. Here comes the difficult part if you can't think out of the box. There are 3 ways that I want you to know how you can increase right now. You can increase like half a smile, or you can increase like half a frown, or you can increase constant, a constant. You can decrease the same. You can decrease, let me do it with a different color, like half a smile. You can decrease half a frown, or you can decrease linearly, like a constant. So here we go. On this first interval right here, we are going to increase until we reach a horizontal tangent of 0. And we're going to reach it right there. Now my question to you is, if I want to increase and come to, whenever I increase, I can either do this, or I can do this, or I can do a straight line. Which one would you end up doing and why? Sad face or frown. Why?
The other two would create cusps.
The other two would create cusps. Okay? You're trying to create a what? Horizontal tangent. So let's do that. Alright? Do you agree with him? Okay? Let's go from now, and I'm only looking over here on my sign tests, 1 to 3. Anything that exists between 1 and 3, or negative 1 3, it's not important. Because the critical important numbers that we found, that's why they're called critical numbers, are negative 1 and 3. So we are going to decrease until we come to a point where we will reach another horizontal tangent. How do we do that?
Can you do both?
You can do both.
Can it change between
Yeah,
smile?
yeah, so you guys are jumping ahead already. I'm going to do a frown first, right? Why do I have to do a frown?
So there's no cusp.
Because it won't create a cusp. It has to keep that smooth curve. It has to come from this horizontal tangent of 0. So it will, let me do a different color, do a frown. And just like you said, somewhere in between there, it has to change from a frown to a smile. So that it will, but it's still decreasing. Both of these are still decreasing. They're just decreasing in different ways. You see that? And then it will reach this horizontal tangent of a slope of 0. Now the last one, and we're going to talk about this point here in a bit. I don't want to jump ahead. It's called a point of inflection. We'll come back to that. We'll see what that is meaning here soon. The last interval, I'm going to what? Increase. Because I came from this horizontal tangent, the only way I can do it is smiling. So it's got to come up like that, and there's your graph. Those values are the important values of this graph that we're looking at as of right now. Do you understand? What questions do you have? Ask good questions if you have them.
I'm just confused on what the middle part is.
As far as the change of direction, the way that we change from frowning to smiling,
Yeah, like
we'll come to it. We'll come to it. Give it a little bit of time.
would there ever be a time where you wanted to create a cusp?
Yeah.
Yeah, well,
There'll be a time where they do create cusps. There'll be a time where they create other things like what? Not endpoints. Vertical tangents. Or what else? Vertical asymptotes. Believe it or not, they'll come and they'll create vertical asymptotes. That's the one that a lot of people forget. That's a lot of people dismiss. But you're going to see one today. Let's see if you can find it. Any questions that we've drawn so far? Yeah. Because when we took the first derivative test and we set it equal to 0, these were the two critical points that we solved. And those two critical points is what it all revolves around. Those are the pivot points, if you will, that show everything partitioned out into sections. Good? Alright, so here we go. Next one. Find the intervals where f is increasing and decreasing. On your test, yes guys, I will try to trick you, especially on your final. I will say, when your final exam, when is this increasing or decreasing? Immediately when you see, whatever you see here, you're going to analyze the first derivative into reality, if you will. So you're thinking to yourself, ooh, I have to find f prime of x. And I have to set it equal to what? 0 and? Fine. Here we go. Anyone derive that for me, please? Oh, not simplified. Not simplified. 2/3.
x squared minus 4 to the negative 1/3 from 2x.
Perfect. Now from there, looking at what I just wrote, anyone please tell me, what is my numerator? 4x, right? Immediately collect all your numerator pieces together. What is your denominator? 3 times, yep, x squared minus 4 to the 1/3. I'm going to set it equal to 0. Now, we talked about rational functions before. You just said it. To find critical points, we got to do this. So we will set it equal to 0 by setting this equal to 0. And we will find the undefined pieces here by setting this equal to 0. And whatever overlap that they share in common, what would that represent? What removable discontinuity or some kind of undefinedness of some kind. That's not necessarily going to be as straightforward and easy to identify. We'll get to that here in just a bit. Let me do this. All right, so here we go. Critical points are at x is equal to what? 0, 2, and negative 2. So we'll put negative 2, 0, and 2. You with me? Alright, so these are my critical points, and it's because I've examined the zeros of the function and the undefined zeros of the function. Let's go ahead and do my number line derivative sign test representation.
So you got negative 2. I'm confused.
So here, for x, set the top equal to 0.
Yes.
What's x?
0.
0, because I divided both sides by 4. Set the bottom equal to 0. The very first thing that you would do, anybody, is what? Divide by 3. And then cube root, no, not cube root. Cube, yeah, cube a 0. What's 0 cubed?
0.
Still 0. So you have this, then you have this, and the square root, you have plus or minus. Plus or minus 2. Now, let's keep going. My number line, the more clearer you do this number line representation, to me, this is your work. The clearer you do it, the more descriptive and careful that you do it. Don't chicken scratch this thing especially. It's going to be easier to graph. It's going to be easier to graph the answer, okay? All right, so here we go. Let me make some room over here. Very first thing that I'm going to put on this number line is what? Yep, negative 2, 0, and 2. How many sign test intervals am I testing? 4. Pick a number, any number. Negative 3. Please put it here. Negative 3 on top is?
12.
Who cares about 12? It's just negative, right? Negative 3 on the bottom is? It's going to be positive, right? So it's going to be 9 minus 5. It's going to be a positive. So the whole quotient is what? Negative. And I'm going to put decreasing. All right, so let's go back a little bit. I think I jumped the gun a little bit. At negative 2, it's going to be 0 or undefined? Undefined. What kind of undefined? We don't know yet, right?
Wouldn't it be asymptotic?
No, they have to be vertical tangent or
Here, let's go back. Is it a horizontal tangent? Okay. So it would only have 3 options. Vertical tangent of some kind, right? Or a cusp of some kind, right? Or an asymptote. Okay? So we'll come back to that. We'll put this for now. We'll discuss it here in just a bit. How about positive 2? Same thing, right? Okay? So undefined. Some of you are getting it. The reason why I'm slowing you down is a lot of you are not. That's why I'm wanting to wait on this. So if you get it, no worries. We'll come back to it. Alright, let's pick another number between negative 2 and 0. Negative 1. So the top is negative. The bottom is negative. So the whole quotient is positive. Now, someone asked me, go ahead.
let's put decreasing and increasing.
Yes, I would prefer that you do. Increasing, just because it's going to help you in the long run. You don't have to write increasing way over here. You write it right next to it so it's easier to graph. And I just started doing this today, and I think it helped a lot better. The flow was a lot faster. All right, positive 1. So we have positive over negative, so it's negative. Someone asked me this today. Once we get negative as the first one, can I just go positive, negative, or just alternate? What do you think?
No.
No, because y'all were already way ahead of that, because you identified what? That something changed from frown to smiley face, and there's that point of inflection that occurred. So you can still decrease 2 different ways. So don't think that there's a pattern and immediately, I don't have to test them, I just do them opposite of each other. Or alternating. So this is decreasing, and then the last one. Something bigger than 3, or sorry, bigger than 2. 3, it's going to be positive, 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 increasing. So, one more thing. At 0, it's 0, right? It's a slope of 0. Sorry I jumped too much. Horizontal tangent. There's your work. Let's start answering. The more descriptive, the more careful you are with that, the rest of the problem is easy. So f of x increases on increases. Yep. Good. Union, right? Please put union. You're at that level. That don't forget that. What else? Yeah. 0 to 2. Yep. Good. Good stuff. Now next answers. Relative max. At x equals 0? No, he's right. So at x is equal to 0, why? F prime of x changes from positive to negative. That's it. Because f prime of x changes signs from positive to negative. Some of you are doing it still. Very little left in this class, but some of you are still trying to interpret the original position function. Don't look at that at all. Not right now. So relative min at what? Negative 2 and 2.
Wait, I thought they were undefined.
It's no. Good question. He says I thought they were undefined. What are undefined? No, the derivative. But are they defined as points?
Yes.
Look, let's go back. We said at negative 2 and 2, their slopes, because of this guy right here, are what? Undefined. But if I plugged in negative 2 and 2 here, what are they? They're defined. What's their output y value? Put negative 2 or 2 in there. What do you get? 0. Do you understand? So the points here on f of x are negative 2, 0, and 2, 0. Those are x-intercepts on the graph. Their slopes are undefined, but their positions are actual values. They're in the domain, if you will. You see it? Again, you're looking at f of x and f prime of x at the same time. Okay? Alright, so let's keep going. So maybe I should have done this before. That might have helped clear up that confusion right there. Let's go ahead and put 0 into this thing. So putting 0 into it, please put in your calculator for me. What would negative 4 raised to the power of 2/3 become? It's like the cube root of 16, right? What is that like? It's like 2.5 to 3 decimal places. Positive, right? Because you squared it. No. Put the negative in the parentheses. That's a common mistake. Put that negative in the parentheses. So it's the cube root of a positive 16. Anyone have that? Oh, I would have given you bonus points. Cube root of a positive 16. I'll just do it myself. Oh my gosh! 16 raised to the... I said third, right?
2/3.
Well, I mean,
Because he squared.
I squared the thing. There we go. 2.520. Okay, so 2.520. 2. What did I say? 520. So this is at 0. Okay, so I have points that are on f of x. Okay, so we'll go to the graph. And we're about to plot them as far as, well, let me finish this over here. Relative min at negative 2 and 2 because? Yes, changes signs from negative to positive. Decreasing to increasing. Okay, now we're ready to graph. Let me make some room because a lot of you got it. Some of you are struggling pretty badly right now. Let's go back. So here's my graph, and I'm going to immediately put these guys on the graph so I know what to go to and what to go from. Okay? So here we go. Negative 2, 0, 2, 0, and 0, 2.5 to 0. See what I did? Okay, if not, please ask me a question. Now, what's up with you? This first one, I'm going to decrease until I reach an undefined of some kind. Okay, so here we go. If I decrease from negative infinity all the way to negative 2, when I reach negative 2 is going to be something of undefined, right? Can it be an asymptote? No. Because of the fact that this existed as a quantitative point. It cannot be a removed discontinuity because of the same reason. So it's either going to be a vertical tangent or a cusp. Do you understand? Because a vertical tangent will exist as a point, closed point. And so will a cusp. So what do you think it is? It will be a cusp, and we'll see here in a minute why. Ready? Yeah. So it's going to be decreasing. Some of you are like, what did he just say that you said yeah to? There it is. I decreased with a frown until I reached the cusp. Now, let's do the other ones. It'll piece together here in just a bit. My next interval, I'm going to increase until I reach a horizontal tangent slope of 0. So it's got to be smooth curve. It's got to be, well, no. If I'm going to increase until I reach this point, the only thing that it can do is a frown. Because if it does a smile, it's going to go back to another cusp. And I can't do a smile also because of what? Well, hold on. Let me change that up. If I do a smile, is that still a cusp?
No.
Yeah. It is a cusp. Because look at that. One is way down here as far as an undefined tangent. The other one is here. They're not the same. So it wouldn't be that. So, sorry I didn't ask the other classes that and I tried to.
Why can't you make it constant?
The reason why I can't make... No, you do increase it too a different way. Why? Listen up. I can't hear you.
Whenever you start to decrease, it would become undefined.
Yeah. There's your answer. The question was, why can't you make it a straight line? Because if you made it a straight line, what would this then become? A cusp. But we don't want it a cusp, we wanted a horizontal tangent. So it can't be a straight line because of that reason. Those are good questions. So it's got to be that. So let's keep going. The next one will be decreasing until you reach another undefined. So it's going to be a frown. And then the last part will be increasing. What would it be? Another frown.
Also, why can't it be a straight line on the outside though? Because then it's already a cusp.
True. There's a... As we learn the second derivative, you'll understand
Is there
more.
any time that there's a straight line within a curve?
Like how?
Like,
Yeah. Is there any time what we did earlier when it's a straight line to a curve? Yes, there is. It's still a cusp. When you learn the test of concavity, which analyzes the second derivative, you may do that at the end of the period today. If not, first thing on the FLs over the weekend, you'll understand exactly what I'm talking about. Okay? Hopefully. Here we go. That's it. We have all our answers. Any questions before we move to the next one? We're not going fast through these because of the fact that there's a lot that I want you to obtain fundamentally with the first ones that I'm giving you. Because when you start to do it on your own, if you've established this pattern, it's a lot easier to do it. Otherwise, it's too intimidating.
So then we just label that as a cusp under the undefined. Is that what we were waiting
Yeah.
for?
Yep. Okay, so let's go. Oh, go ahead.
So we know that negative 2 and 2 have to be undefined because we said them equal undefined.
Yes, look, at negative 2 and 2, guys, what's undefined? What is undefined? Derivative. The slope is undefined, and we saw that right here when we did the derivative sign test. But ultimately, the points are defined because over here on the f of x function, we had them as quantitative points. Okay, next one. Let's see. Let's go with Kyle. Start us off. Go ahead and start us off.
Yeah, you do question.
Okay, so what is that? F prime of x equals?
2x minus 1 over 2x
Okay,
minus x squared,
okay.
2, and then 2, and then in the denominator it's 2x minus 1 squared.
Perfect.
Yeah.
Now, what would y'all do here? Anyone? Simplify, yes, definitely simplify. I would simplify, not necessarily going for the setting them equal to 0 yet. And you'll see that here in just a bit. Distributing this would give me 4x squared minus 2x. Minus 2x squared if I continue to do the top. Okay, combine like terms. 2x squared minus 2x. What am I going to GCF? 2x. So ultimately, oops. This is the numerator. Do you agree? Okay. The denominator is still this. So some of you are looking down while I'm asking questions. That was a fear of the notes, but no worries. Just make sure that if you do have a question, please ask it. Here's my derivative. My aim is to set it equal to what? 0 and undefined. Let's get the zeros. Not the undefined critical points, but what are the 0 critical points? 1 and 0. So here we go. Critical points. X is equal to 0, oops, and 1. What are the denominators? 1/2. See it? Okay, so now we're going to do our number line representation. And what goes here? F prime of x. Good. This is a first derivative analyzation. It's not anything else. It is the first derivative. So it's 0, 1/2, and 1. What first number would y'all choose? -1. Here we go. Using this, I have negative, come on, negative over positive. So the whole thing is a positive. What can you tell me about the denominator in this piece? It would always be positive. Why? Because it's squared. If it's always squared on the bottom, it's always going to be positive. Do you understand? If it was something like this, that doesn't necessarily mean that it would always be positive. It's where the squared is located at. PEMDAS says at the very end, whoops, you're going to square it and it becomes positive no matter what. So let's do the next one. Let's do positive 1/4. So positive, negative, and positive. So negative. So increasing, decreasing. Let's do 3/4. So positive, negative, positive, still negative. There it goes to what y'all jumped the gun way long ago. It's not alternating, it could be decreasing and decreasing. It'll further be solidified when we learn the test of concavity using the second derivative. Okay? And we'll get to that soon. And the last one, let's do 2. Positive, positive, positive. So it'll be increasing. Okay, I just got the details or attributes of f of x. So if you wanted to, you could do that if you wanted. Okay. Now let's go over here and identify 0. Critical point is, what's 0's critical point? Horizontal tangent. Yep. 0, horizontal tangent. How about 1/2? Undefined, and we don't know yet, right?
Oh, really?
Why is it a vertical tangent?
Because it keeps decreasing, so it wouldn't be like a minimum max.
Nope.
See, it says
Nope. Okay, we'll come back to it. We'll come back to it. This is why I always keep this as a question mark for now. How about 1? Anybody? So it's 0 and it's going to be a horizontal tangent. Here we go. We're going to come back to this question mark on undefined. Because here's the thing, and I want you to see if you can answer it right now with just me asking. If the derivative is undefined, that means when I come to that point, how can I show that the derivative is undefined? It can be a cusp. It can be a, not a horizontal, a vertical tangent, or a vertical asymptote. Which one of those can not exist in the domain? The asymptote. The other two have to exist as a point. Do you understand? They have to exist as an actual numeric value that you get here. So let's plug it in right now. 1/2 squared, 1/4. 1/2, you're dividing by 0. What is the value of it if I put it into the position function? Undefined. So what is this going to be right here? No, not a removable. A vertical asymptote. We'll come to that. I see what you're saying.
How would you know which one?
Because it's not going to be removable because from pre-cal knowledge, there's not a two-of-a-kind pair. One on top and one on bottom that you can just factor out. That's how. You know what I mean?
I don't understand that.
Okay, go back to pre-cal. If I had something like x and then x minus 1, and it was like this on the original position function,
Okay.
at x is equal to 0, that's where it would be
So-
undefined because this is a removable discontinuity.
Yes.
I understand that, but like, didn't you just say it couldn't be a?
I just said it couldn't be a vertical tangent nor a
Oh, I
cusp.
thought you said S.
No, it can be a vertical asymptote. So this is a VA. Okay, so here we go. Let's get these points first of all. F of x, y's. F of x, we have 0, what? We have 1/2, and we have 1. What is the y value if I plug in 0 into the original? 0. What did we say it was if I plug in 1/2? Undefined. So this is like, yeah, I'll just write it like that. And then if it's 1, what would it be? 1. Okay, those are the pieces on the graph that we're going to look at primarily first. Okay? So now let's go ahead and go, we're going to jump the gun a little bit. We're going to graph it first and then we'll describe it and you can write it in your notes, okay? 0, 0. At 1/2 is going to be undefined of some sort and we came up with the VA. So here's your VA. And at 1, it's going to be 1, 1, right? So we'll say that's 1. So here we go. And I should color those all the way in. You ready? Alright. On this first interval from negative infinity to 0, I'm going to, let me call on people. And start us off. I'm going to do what? Increasing how? Frown, smiley, or a straight line? Frown, right? Why? Because we're going to horizontal 0. Nice. And no worries if anyone answer, that's good. So we're going to, because you're understanding. Alright, so I'm going to frown up to that horizontal tangent. Now anybody, I'm not going to call on people's names. From 0 now to 1/2, I'm going to what? Decrease until I reach the vertical, vertical asymptote. So what would you suggest? It's got to be a frown.
It's gotta be front and then it's gonna, wait, but it's over.
Check it out, check it out. 1/2 to 1, I'm going to do what? Decrease to a slope of 0. Smiley face. I'm going to decrease until I come to a slope of 0. There's your vertical asymptote. And at the very end, I'm going to increase with a smiley face. There's your graph. Now, here are your answers. You ready? You would justify this as per first derivative test. So go ahead and write it on yours. Per first derivative test, f of x increases and decreases on the following. We were going to say on, not at, because we're good like that. Increases on negative infinity to 0, union 1 to infinity. Who can tell me why I decrease? What would you do it?
0 to 1/2 and
Union 1/2 y.
Why do you not say 0 to 1? Because
Because
it's undefined. Yes, and there's no sign. It doesn't have a negative sign at 1/2. Okay, so don't include it. It's a huge argument that math teachers and math students go through every year. And they keep saying, it doesn't matter. It's still decreased with that prehistoric description definition, which is right here. And we're like, no, we're not teaching pre-cal, we're teaching calc. So after 2 years, Mr. DeVito has finally given it. Yes, so you decrease by showing 0 to 1/2 and 1/2 to 1. Are we good? All right, so 0 to 1/2 union, 1/2 to 1. And then we will say relative max at x equals 0, y. F prime of x changes signs from positive to negative. It's a union, you're far away.
Looks like a 0.
It's not.
it's almost close.
It was pretty close.
How's that?
That's better. I was just confused.
Okay, so now let's look at, I'm joking. The next part.
I thought it was smiles. There you go.
There you go, your concave ups. Next part is relative min occurs at x equals 1. Don't just put 1. X equals 1 because f prime of x changes from negative to positive. Are we good? Easy, right? Scale from 1 to 10. Where are we at right now?
6.
It feels like a
6 or 5?
7.5.
It's a good number.
What is it?
I think a 4, but
Oh.
yeah, I was trying to see where you're at.
Well, we understood.
Yeah, how well do you understand it? Like, oh my bad, no. How difficult is this? Like, related rates is a 10. Where does this lie? Really, like a 2?
Yeah.
Okay, good. Okay, we're good. All right, here we go. Not yesterday. Shh. Not yesterday, but today, we said f prime of x was. That's why I erased it.
It's
F prime of
increasing.
when f prime of x is positive, then what is f of x increases. Remember, the tattletale will tell you what one level of the derivative up is doing, vice versa. When f prime of x is negative, f of x is decreasing. When it's 0, f of x is constant. And you could be constant like this. Yes, wait. And you could also be constant like what?
Constantly
No, you
decreasing.
could be. It's
Come on,
it's
guys.
any linear.
Like,
As long as you're not
is it constant?
Positive is increasing. Negative is decreasing. If it's 0, it could be constant the way I showed you. Or what's another way? Like a point. No, a point. A point. A point. A point.
Ian doesn't need more
All right, here we go.
Ian is fine where he is.
Next one.
Give it to Kyle.
Shh. If I'm looking at first derivative test, changes from positive to negative, negative to positive, f of c is a relative max, not just a max, and a relative min. So just a little review. We just did it, so we didn't have to spend too much time on that, thankfully. Let's move on. This is different. This is different in the fact of you're still using first derivative test stuff. You're still using all that we did, only you're going to be given different information in a different way. So let's see how you interpret what you see. Piecewise function. I know you can graph these by yourself without looking at the calculator. That's not the point of this exercise. The point is being able to do it by analyzing the first derivative. Because you won't have easy ones like this on the test. But the stuff that we're going to interpret from f prime of x, that's what we're trying to start off with, a piecewise function. Very first thing that I would tell you to do is find the derivative piecewise. Okay, so we have 2 and we have 2x. Now some of you struggle. If you're like me, at the level that you're first exposed to these, you would struggle to really see what this domain is representing. So to help me out when I was in your shoes, I would do this. -1, -1, and then I would do this, and I would do, and you're going to see why here in just a bit, that. So that I know what intervals I'm looking at. Okay? So, what do you remember I told you to do a long time ago when you saw something like this on a piecewise function? What if? Okay, so the what if. The what if x is equal to -1. What point would I have on the top? -1, -1, right? What would I have for this bottom function? -1, -1. So the same thing. Now, since those two meet and they're the same, we would say it was what there? Come on, we would say it was what? Continuous. We would say it would be continuous there, not differentiable, because we're not putting this in the differentiable piecewise function. They're the same points. So they come to that ET moment, if you will, continuous. So the point exists. The point exists. It's not going to be an asymptote. It can exist as what? A cusp. What else? A horizontal tangent? Or a vertical tangent. It's existing as a point. Yeah, we'll get to that in a bit. You're jumping ahead, but it does exist as one of those three. Now let's analyze this one over here. What if? X is equal to -1. If x is equal to -1, I'm not going to do this. What could I write here to denote both of these piecewise? Think about it. How do you think I would want you to write this that describes what's going on? Let's do the first one. What would you write? Nice, Bree. F prime of -1 is equal to 2. If it's equal to 2, what would you write for the other one? F prime of -1 is what? -2. Are those the same? No, because they're not the same. There we say it's what? Not continuous. Not differentiable. Because you're looking at the first derivative. There's no ET moment coming and converging to the same value, so it's non-differentiable. Okay? So write that in your notes for me, please. Non-differentiable, continuous. Yes, continuous. It's defined as a point. Okay, so let's go ahead and let's look for critical points. What critical points do you see right now? That's when you're setting the derivatives equal to 0. X equals 0. X equals 0. Look, 2x, it's like f prime of x. It's a different format. You're not used to seeing it. Write it like this. Set it equal to 0. So x is equal to 0 is one of the critical points. Do you see any more? The 2 is not undefined. The -1 is undefined. Why? Because it's non-differentiable. It's non-differentiable. One has a 2, one has a -2. So it's going to be non-differentiable. So if I look at that, I'm going to say -1, even though I didn't set it equal to anything. What I really set equal to, what I really set x is equal to -1 equal to is undefined. That's how I figured out that this is also going to be a critical point. Okay, that one's a harder one. All right, here we go. Sign test. -1 and 0. F prime of x. Do I have a factored equation that I'm going to plug these values in? Nope. The only thing that I have is right here. So let's plug in something in this interval. What do you want to pick? -2. Well, -2 is over here. So what is it, positive or negative? Positive. Always, right? Because it's a positive what? 2. So that'll be positive. Let's pick negative 1/2. Negative 1/2 is going to be what? Negative, right? Because negative 1/2 lies right here. When I plug it into this equation, 2 times negative 1/2 is going to be a what? A negative value. So there we have it. Something to the positive or right of 0. Let's pick what? 1. So 1 is over here. We put that here. 2 times 1 is a positive. Good. So we have increasing, decreasing, and increasing. At negative 1, what did we say it was? Undefined. And at 0, we said 0. Horizontal tangent. Now think about this. I want you to increase and then decrease. So that's a relative max. What do you think it would be? A vertical tangent? Yes or no? No, because you're not increasing, or decreasing, decreasing. These are changing. So the only thing that it can be is a what? A cusp. So here we go. Let's start graphing it. The very first thing that I want to graph are the ones that we defined as points. -1, -1. And that was it. What was the other thing that we decided to graph? No, that's it. Never mind. So on this interval, we are going to increase until we come to a cusp. And when we come to that cusp, we're going to be at this -1, -1 point. How should I increase? Constant, right? Why can I not do a curve? What?
There's no X, yeah. I mean, if you
Oh, that's what I was looking for. There's no X. If there's no X, it's going to be just a straight line. If there's no variegating variable, it will be a straight line. Okay? So this will go straight to that. Now let's keep going. From -1 to 0, I'm going to decrease up until I come to a horizontal tangent. How can you decrease from there to go to a horizontal tangent? A smile. And where am I going to stop? That's the only point that I did not write here. What's that point? Come on. You said it from the other example. The y-intercept. Put the y-intercept on this graph. Where would the graph be at? So 0 is here. So it'd be at -2. 0, -2. Okay, so I jumped the gun a little bit on that y-intercept, but you see now why it's important. No worries. Yeah. Okay, so from 0 to infinity, I'm going to increase with a smile because I'm coming from a horizontal tangent. And guys, let's go back. Does this look like what we know this to be in those specific intervals? Yeah. So here we go. Everything is satisfied. The cusp, the horizontal tangent, everything. Here are your answers because we're running out of time. We're going to put per first derivative test. F of x is increasing on -infinity to -1, union 0 to infinity. Some of you already wrote it down. I can see that. F of x is decreasing on -1 to 0. Are we good? And then the next one will be relative max at x is equal to -1. Because f prime of x changes from that positive to negative. Please put f prime. And then relative min at x is equal to 0 because f prime of x changes signs from -1, or sorry, from negative to positive. Are you with me? And then the last part, no, that's it. The only thing that I realize now that I have not been telling you is when I say f of x increases on -infinity to -1, union 0 to infinity. I should put a because. I don't know why I haven't been doing that. I should put a because. What because comes after this? Because f prime of x is what?
Continuous.
No? Positive. Okay? That That one is a little bit forgiving, and I think they may forgive it, especially if you mention it in the relative max and min, that you know the difference between positive and negative. I'm going to require that. I want you to write that down, okay? So there is a lot of, this is what gets you in this unit. But you know what? It's repetitive justification. It's the same thing. Okay, so it's really not that bad. So it's increasing because f prime of x is positive. A couple more examples and we are done for today. Alright, so shake it off a little bit. This is where a lot of people struggle. And do I dread showing this like I do dread the dreadful related rates? I do. This is to that magnitude because when you get it, you have it for the whole year. When you don't get it, most students will not try to get it until they're reviewing for the AP exam. Okay, and they're stressful. I'm looking at f prime of x. This is not f of x. Okay, so look at that and say it to yourself in your head if you want. I am not looking at f of x. Going back to our analogy when Ian was f of x and Harrison was f prime of x, this is a Harrison graph. What is our goal? Our goal is to interpret what does f of x possibly look like from what this is showing us. Exactly, that's the hard part. How does f of x look like from what this is showing us? We're going to get good at this in about 2 days. Okay, here we go. Identify the intervals on which the graph of f increases and decreases. When you see that, get in a little bit of an autopilot mode. And I need to find when f prime of x is what? Positive and negative. Get this, it's an f prime graph. It's already there for me. So everything that is above the x-axis, f of x will be increasing. F prime is positive. Anything above, and a lot of you got it, and that's good. Anything above the x-axis is positive. And if that's f prime graph that is saying that, that means on f of x, which is invisible right now, we know it's increasing on those intervals, at least. Okay? Just like you did the number line test from before. Okay, and if you are struggling with that, there's maybe 2 of you right now, you could put -3, 1, and 4. And it would be -3 to 1 is positive, and 4 to infinity is positive. And these are going to be negative and negative. You see it? Now I think you got it a little bit better. Okay? Why did I list these 3 numbers out? They're the zeros, they're the x-intercepts, they're the critical points of what? F of x. Not f prime of x. They're the critical points of f of x. How do you find a critical point? Well, take the derivative, set it equal to 0. Those are your critical points. Yeah, then you find the value. Okay? Alright, so here we go. Below are negative. So I would say f of x increases on -3 to 1 union 4 to infinity because f prime of x is positive. Or you can write it like this. Instead of writing out is positive, they prefer you to do that. But please don't read that as because f prime of x is greater than 0. No, don't think of it like that. Think of it as f prime of x is positive. Okay? And then f prime of x decreases on what? -3 union 1 to 4 because f prime of x is negative. Negative, right? Okay. All right. At -3, 0, and 4. Critical points. It could be a cusp. True or false? False. Why? Because the graph tells us their values are what? Horizontal tangents. This right here is a horizontal tangent, guys. Why? Because its derivative, otherwise its y value on this graph of the derivative function is what? Quantitatively, 0. Quantitatively, this is 0. Quantitatively, this is 0. What would it have to be on the f prime for it to be a cusp? Undefined. A removable discontinuity of some sort, right? Some sort, it would be an undefined. This would show you that is a cusp or vertical tangent or something on that graph. You see it? Alright, so here we go. Estimate the values of x at which the graph has a relative max. Where's the relative max? X is
X
equal
equal
to 1. Why?
Because it's changing.
Well, no. Because what is changing?
F
Because f prime of x changes signs from positive to negative. Where's the relative min? X equals negative 3 and 4, because f prime of x changes signs from negative to positive. And we'll stop there. Awesome job today.